Hello student, in this video lecture we are going to see another example to develop a stiffness matrix. Generate a stiffness matrix for the coordinate shown in figure. So, this is our beam. It is a propped cantilever having length 2L and flexure rigidity EI is constant. So, this propped cantilever is provided with two coordinate direction at the middle of the beam at joint B. So, first coordinate direction is a transverse displacement along y direction. Then second one is a rotation, clockwise rotation at joint B. The first and foremost thing to develop the stiffness matrix is, so first we need to determine the order of the matrix. The order of the matrix is equal to number of coordinates chosen. So, in this case there are two coordinates. So, the order of the matrix is equal to 2. The stiffness matrix is a 2 by 2 square matrix. Then, so first thing, the first step is restrain the structures in the coordinates chosen. So, in this problem they shown two coordinates, one is delta y direction, another one is theta, clockwise rotation theta. So, first thing we have to restrain this delta y and theta at joint B. So, for this we have to provide the fixity at joint B. So, with the help of this fixity we will restrain delta y and rotation at joint B. Then second step is develop the first column of the stiffness matrix. It is a 2 by 2 stiffness matrix. So, in order to develop the first column of the stiffness matrix, we have to allow unit displacement in the direction 1 only, but the structure is restrained in the direction 2. So, first direction 1 is the transverse displacement along y direction. So, in the restraint structures, in the above restraint structure, this is our restraint structures. So, this is our restraint structures. Now, allow unit displacement, unit transverse displacement at joint B. Okay. So, now the support is like this. Okay. So, now the structure transform into like this. So, we allowed transverse displacement at joint B, delta y is equal to 1. Now, the split the structure into two part, one is AB part. So, first one is AB part, second one is BC part. Okay. So, allow displacement delta is equal to 1 on the both the part. After allowing unit displacement in the transverse y direction, now measure the force induced in a structure. The force induced in a structure, it may be axial force, a shear force and moment. Okay. So, our first coordinate direction is the force in y direction. So, therefore, we have to measure the vertical reaction at joint B. Then second coordinate direction is the moment, clockwise moment at B. So, for this again we have to measure the induced moment in joint B's. Okay. So, for the left off portion is the AB portion. So, now apply transverse displacement delta is equal to 1, the induced moment. Okay. So, if the both ends are fixed and one of the support, one of the fixed end is sinking with the delta, means the induced moment is 6 delta by L square. Okay. So, sinking is in downward direction. So, therefore, induced moment is anti-clockwise moment, that is 6 delta by L square. So, this side also 6 delta by L square. For the BC portion, so one end is fixed, okay, but other end is pinned support. So, therefore, the induced moment at the fixed end is equal to 3 by L square, at the pinned end is 0. So, that is represented in this diagram. Okay. So, this is a separate diagram. Now, determine the support reactions, that is the vertical reaction. Our aim is to determine the vertical reactions at B and induced moment at B. So, only these two values or necessary. Our stiffness matrix 2 by 2 stiffness matrix. So, first coordinate is the force in vertically downward direction at joint B, second coordinate is the moment. So, that is why we are going to concentrate on VB and MB value. Okay. So, we already find the MB value for MBA is equal to 6A by L square, MBC is equal to 3A by L square. So, finally, MB is equal to, so net of these two, MBA plus MBC. Now, we are going to determine the support reactions at B. So, for this we apply equilibrium equation. So, first apply equilibrium equation, summation of moment about A is equal to 0 for left portion, AB portion. So, apply equilibrium equation, the reaction RB1 is equal to 12 EI by L cube, it is in downward direction. Okay. Then apply another equilibrium equation for BC portion. So, summation of moment about C is equal to 0. Okay. So, from that equilibrium equation RB2 is equal to 3 EI by L square, just simply we apply equilibrium equation RB2 is equal to 3 EI by L cube. So, finally, the stiffness matrix, stiffness element K11, that is force induced in the direction 1 due to unit displacement in the direction 1 only. Okay. So, that is the first one is the force, first coordinate direction is the force in downward direction. So, now measure the reaction, RB reaction is the K11. So, RB1 is equal to 12 EI by L cube is in downward, then RB2 is equal to 3 EI by L cube, it is also downward. So, our coordinate direction also downward. So, therefore, it is taken as positive. Therefore, K11 is equal to 12 EI by L cube, that is RB1 plus RB2. So, it is 15 EI by L cube. Then K21 is the force developed in the direction 2 due to unit displacement in the direction 1. Okay. So, that is net value of MBA plus MBC. Okay. So, our coordinate direction is clockwise movement at B. Therefore, the clockwise movement is taken as positive, anti-clockwise negative. For BC portion, it is moment is clockwise. MBC is equal to 3 EI by L square, but MBA is equal to minus, it is an anti-clockwise moment 6 EI by L square. So, therefore, net moment is equal to minus 3 EI by L square. The first column of the stiffness matrix is 15 EI by L cube, then minus 3 EI by L square. Then next step, next we are going to develop the second column of the stiffness matrix. For this, we have to allow unit displacement in the direction 2 only, but direction 1 is restrained again. Okay. So, now I apply unit rotation. So, second coordinate direction is the rotation direction, rotation in clockwise direction, rotation in clockwise. So, therefore, we allow a rotation at joint B in clockwise direction. So, it can be rotated like this, the structure can be rotated like this. Now, split the structure into two parts, one is AB part, another one is BC part. So, general moment, if the both the ends are fixed, this is fixed, this is fixed. Now, allow rotation of joint. Now, allow rotation of joint, theta means the induced moment at B is equal to 4 EI by L. For A, it is 2 EI by L. Okay. So, this rotation anti-clockwise moment, induced moment also in anti-clockwise, both the support anti-clockwise moments are induced. So, in this case, this joint B is the fixed joint. Now, we allowed unit rotation. So, therefore, induced moment at joint B, that is MB1 is equal to 4 EI by L. So, that is in clockwise direction. Then MA is equal to 2 EI by L. For BC portion, so B is fixed end. Okay, fixed end we allowed rotation, but C is a roller. So therefore, induced moment is equal to 3 a by L at B. MB2 is equal to 3 a by L, then MC is equal to 0. Okay. Now determine the reaction RB, that is RB1 plus RB2. So in order to determine RB1, we apply equilibrium equation for AB portion. So that is summation of moment about A equal to 0. Apply summation of moment about A is equal to 0. So which gives RB1 is equal to 6A by L square. Then RB2, it is determined from applying equilibrium equation for BC portion. Okay. So the summation of moment about C is equal to 0. So which gives RB2 is equal to minus 3A by L square. Then net moment at B is equal to MB is equal to MB1 plus MB2. That is, MB1 is in clockwise direction 4A by L, MB2 also is in clockwise direction 3A by L. Okay. So MB1 is in clockwise direction 4A by L, MB2 also is in clockwise direction, that is 3A by L. Totally MB is equal to 7A by L. Then RB is equal to RB1 plus RB2. So RB1 is in upward direction. Okay, that is 6EI by L square. RB2 is equal to RB2 is in downward direction, that is minus 3A by L square. So net reaction is equal to 3A by L square in upward direction. Then K12 means a force produced in the direction 1 due to unit displacement in direction 2. So our coordinate direction 1 is in downward direction, but the induced reaction RB is in upward direction. Therefore, we have to use a minus sign, minus RB is a K12. Then K22 is equal to force developed in direction 2 due to unit displacement in direction 2. So unit 2 coordinate is a moment coordinate or rotation coordinate is in clockwise direction. So therefore we have to consider in moment at B as K22. So K22 is equal to 7A by L. The final stiffness matrix is this: 15EI by L cube minus 3A by L square minus 3A by L square, 7EI by L.